Okay, so now what we're going to do is we are going to talk about adding forces in space, meaning three-dimensional. Okay, so a force in space is in all three dimensions, x, y, and z. So notice how over here on the right, how our x, y, and z axes are, right? So x and y are like our flat piece of paper, and z is coming out of the paper, more or less, is how we'll be drawing this. Okay, so what we're going to do is we are going to look at this force F, wherever my mouse went. There it is. Okay, so we're going to look at this force F, and it's projecting somewhere out in space on our coordinate system that's shown. Okay, so to define F, we are going to make a plane, okay, out of O, B, A, and C. That is the plane our force lies on. Okay, and it passes through the y-axis, so its orientation can be defined by the angle phi, the Greek letter phi. So that is this right here. This is the Greek letter phi. That is how far away that plane is rotated from the xy plane. Okay, so it's like if I took this force, drew it on the xy plane, and then took my paper and pivoted it out toward me at that angle. So we can also further define this by angle theta sub y. How far is it tilted from the y-axis? Okay, so what we can do then is we can break this force up into two pieces. Okay, so right now this force can be broken up into a horizontal part, this F sub h part. Okay, and we can find the y component part if we know what theta y is. Okay, that is our x and y, or our horizontal and our y component. Okay, so, but notice that horizontal, this F sub h, is laying on the x and z plane. Okay, so we need to know what those components are. Okay, so since it lays on the xz plane, that angle phi right here that we figured out earlier, we can figure out the x component and the z component. Those three components put together is what defines our F. Okay, so how we did that, we took that y component, right, and use theta y to break it up into y component and that horizontal component. Okay, and then to get our x and z components, we took that horizontal vector and used cosine to find the x component and sine to find the y component. Okay, so that's all that we did. We took that horizontal component, multiplied it by the cosine of phi. Okay, and all I'm doing is substituting f sine theta y in for that f horizontal. Okay, and the same thing here. So now, since the force F has been resolved into three rectangular vector components, we can apply the Pythagorean theorem to the triangles OAB, so OAB, and OCD. Oh, here we go. Sorry. OCD. Okay, to those two triangles. Okay, and then when we eliminate, so all that we're going to do is we know that f squared equals the side OA squared, okay, which is equal to that OB squared plus this side squared. Okay, just our triangular, our sides, right? So f sub y and f sub h. Okay, and that horizontal component we know consists of f sub x squared and f sub z squared. So what we're going to do is all we're going to do is eliminate the f sub h from it, and we know that to find the magnitude of that force, all I've got to do is take the x component and square it. Oops. Y component and square it, and the z component and square it, and take the square root. So it's just like the Pythagorean theorem in 3D, right? You're taking all three of those components and applying the Pythagorean theorem to them. Okay, so this new relationship, sometimes it's easier to see if we put it in a box. Okay, so all that we're going to do, and then our three components are just the edges. Okay, so if we had f sub z, there is one side of our box, f sub x is another side of our box, and f sub y is another side of our box. And notice the force that we're finding is going from the back left corner to the front right corner. Okay, so the angles, okay, so that force F is just represented by the main diagonal of the box. Okay, as are the three triangles used to derive the formulas for the three vector components. Okay, so now what we've got is we've got three different angles. These are called direction cosines of the force. Okay, so all that means is the shortest angle from the x-axis to the force F, that is theta x. Okay, it's just the angles that are formed with the x, y, and z axes. Okay, so this one is theta y. Goes from the force up to the y-axis. Z is the same way, it just goes to the z-axis. That's theta z. Okay, so we can also find the components by using those direction cosines. Okay, so if we know the force F and we take and we know what theta x is, okay, what theta x, theta y, and theta z are, we can find the components. Okay, and now that we have the scalar components, we can write in vector Cartesian notation for F. Okay, we just get f of x sub I plus f of y sub j, or j hat plus f sub z k. So the direction cosine that f forms with each axis should be measured from the positive side of the axis always, and it should be between 0 and 180. That's when cosine is positive. So therefore an angle with a number less than 90 will be on the positive side of the axis, and an angle with a number greater than 90 is going to be on the other side of the axis. So here, all of these should be below 90 degrees. Okay, so if we take and substitute the expression obtained for the components of f in our previous equation, okay, so that's what these are right here, okay, in our previous two spots. Okay, that is how we can get f. So all that this does is this equation shows that f can be expressed as the product of a scalar and what we call vector lambda. Okay, and what we call lambda is the unit vector along the line of action. Okay, and what we can get is we can get lambda equals, it's just the different direction cosines added together. Okay, and notice they're all going to be less than 1. All three of these are going to be less than 1. Okay, so these values of the three angles are not independent. Okay, so remember that the sum of the square of the components of a vector is equal to the square of its magnitude. So in this case, if we added all three of these together, okay, so if we took the x component and the y component of lambda and the z component of lambda and added them together, they're going to equal 1. Okay, and if we do some more substitutions, we can show the relationship directly between the direction cosines. Oh, darn it. Okay, so if I square cosine theta x, yeah, right, cosine squared of theta y and cosine squared of theta z, that should all equal to 1. All I'm doing is substituting this in for this and squaring it, this in for this and squaring it, and this in for this and squaring it. That's all that we're doing. Okay, so that means when the components f sub x, f sub y, and f sub z are given, which a lot of times they are, okay, and we calculate the magnitude of f using that Pythagorean theorem, we can figure out the direction cosines for them. Okay, and that's just by taking pretty much, right, the adjacent over hypotenuse for each triangle that's formed. Okay, so if I drew and made a right triangle here, right, between F and the x-axis, right, I'd have adjacent over hypotenuse. And if I did that for each one, that's exactly what I would have. Adjacent over hypotenuse, okay, for each one. Okay, so let's maybe see if we can figure this out a little bit more. Okay, we are just going to do concept application 2.5, so you can kind of see how this works a little bit. Okay, so concept application 2.5, this is on page 51 if you want to follow along. Okay, we have a force that has three components to it. F sub x equals 20 pounds, F sub y equals a negative 30 pounds, and F sub z equals 60 pounds. We want to determine the magnitude of the force and the angle and the direction angles that it forms with each axis. Okay, so we are going to have F, oopsie, that is not what I wanted to do. Okay, so F sub x is 20 pounds. F sub y is equal to a negative 30 pounds. And F sub z, okay, is going to equal 60 pounds. So we might just take a quick look at what this might look like on an x, y, and z axis. Okay, so here's my x, my y, z or x-axis, and my z is going to be coming, my positive z-axis is going to be coming out here. Okay, so let's just draw these with kind of a different color here. Okay, so if these are my axes, I've got f of x, the component is 20 pounds, right? So that means I have a vector going this way, that's 20 pounds. F sub y is a negative 30 pounds, meaning that's going to go straight down. That component is going to go straight down like that. Okay, and z being 60 pounds, it's going to be out along this way. Okay, kind of like that. So remember, this forms all the sides of my triangle of a box, right? Okay, so if I want to draw that box, just so we get an idea of what it looks like, let's use orange. Okay, so here's one side of my box, right? Oops. Let me touch there. Okay, if we kind of finish our box here. Okay, that means our vector should go from this corner up here. That's kind of straight down to that corner. Okay, so that's kind of what it's going to look like when we actually, if we actually drew this. Okay, now kind of